Hello everyone, thanks for attending my today's presentation. Today's presentation topic is multi-channel active noise control with special derivative constraint to enlarge the white. My name is Shi Dongyuan, coming from Nanyang Technological University in Singapore. In today's presentation, I will firstly introduce current problem of the active noise control technique. Then I will report our proposed method to solve this problem. Finally, I will introduce the simulation result of this new idea. What's the active noise control? Active noise control is a technique which uses the note speaker to generate the anti-noise wave to cancel the disturbance at the error microphone. This technique has been widely applied in many areas, such as the ventilation ducts, vehicles, headphones, and so on. However, most of the active noise control algorithms aim to control the signal of error sensor, which needs the local noise attenuation only around error microphone. To solve these problems, many researchers use the wave-film synthesis and the boundary surface control. The other researchers use the sound field control based on wave number domain. The other researchers also use the spatial ANC technique. These methods can effectively gain a satisfactory noise control role in the desired position. However, these methods usually focus on the noise cancellation in an enclosed region and require many secondary sources and sensors. In this presentation, we propose a new method which uses the spatial derivative constraint to increase the quieter role of ANC while using least number of error microphones. In this slide, the figure 1 shows the block diagram of a multi-channel ANC system, which has the K reference microphone, LO secondary source, and M error microphones. In these figures, the W and the C denotes the control filter and the secondary pass matrix. So the general task of this control system is to find the optimal control filter W to make its product with the secondary pass matrix equal the primary pass matrix as shown in equation 1. This equation is the system control equation. In this equation, the X, Y, Z denotes the spatial coordinates of error microphone. However, the solution of equation 1 only can cancel the noise at the error microphone. For example, the figure 2 shows the sound film of the M's error microphone. The conventional control filter can only achieve a very small noise reduction performance around the error microphone. To increase this noise cancellation rate, we have in the noise control and its neighborhood regions, such as this N vicinity point. To do this, we bring in a special derivative constraint, which in this method, we force the N vicinity points derivative equal to 0, as shown in equation 2. However, in practice, it's difficult to directly calculate the special derivative. So we replace equation 2 with a special different constraint, like equation 3. In this equation, the T denotes the distance between the error microphone and the vicinity point, and the CMLI denotes the transfer function from L's speaker to the I's vicinity point near the M's microphone. Then by integrating the spatial difference constraint with the old control equation, we can gain a new control equation for the whole system, as shown in equation 5. In this equation, the new secondary pass matrix and the primary pass matrix are shown in following expression. To solve this equation, we firstly need to get the new arrow sensor vectors, which is given by the equation 6. In this equation, the d omega denotes a disturbance vector. It's a product of the primary path matrix at the primary source. The system cost function is also defined as the mean square of the arrow signal. By using the negative gradient of equation A to update the coefficient, the recursive equation of the control filter at the sample index n is obtained at equation 9. By taking the inverse FFT of this equation, we can gain its equivalent time domain expression as shown in equation 10. We finally replace the mean value of equation 8 with the instantaneous value to yield the new control filter algorithm, which is given by the equation 11. In this equation, the first term is as the same as the multi-channel FXMS algorithm, and the second term belongs the derivative constraint. To test the performance of this new algorithm, we also carry a 2D simulation on a small noise chamber, as shown in figure 3. Inside this small noise chamber, there is the primary source. A reference microphone was placed close this primary source. Another 2 secondary sources are put outside this noise chamber. The opening slit of this chamber is 16 centimeters wide, and the 2 arrow microphones keep 14 centimeters far away from this slit. And the T in this figure denotes the distance between the vicinity point and its arrow microphone. And the 2 arrow microphone distance is 13 centimeters. So in that simulation, the frequency of primary noise is set at 700 Hz. The figure 4 shows the sound pressure level distribution of noise propagating from the noise chamber into the free field, where the red angle denotes the position of the arrow microphone. The figure A shows the case without control. And from the figure 2, we can know the multi-channel FXMS algorithm with 2 arrow microphones just can gain a very small noise control area. However, when we increase the number of the arrow microphones to the 6, the multi-channel FXMS can gain a better global noise reduction performance. Then for the proposed algorithm, it just can use the 2 arrow microphone to achieve similar noise reduction as the multi-channel FXMS algorithm. When we increase the distance between the arrow microphone and its vicinity point, we can find the global noise reduction of the proposed algorithm also reduced, such as shown in figure E and figure F. The figure 5 shows the contour of noise reduction level distribution in the free field outside the noise chamber. From the figure A, we can confirm the multi-channel FXMS algorithm with 2 arrow microphone can only achieve very small noise control area. It's just get the local noise control. While the proposed algorithm can only use the two arrow microphone achieve even better noise reduction performance than the multi-channel FXMS who use the 6 arrow microphones. When we increase the distance between the vicinity point and the arrow microphone, the deep noise reduction role of the proposed algorithm also reduced. So from this simulation, we can find the proposed algorithm can enlarge the quiet role by using this arrow microphone than a conventional multi-channel FXMS algorithm. So that's all. Thank you for your listening.